we will continue our afternoon session with our valuable Professor Kadir Durak from Özyeğin University. So Kadir is a distinguished position in Turkey. He is one of the rare academicians who is trying to do quantum technology, both from practical point of view and take challenges experimentally, as well as a good understanding of theoretical quantum communication as well. Today, we are going to listen his lecture, and we have only one talk in this afternoon session, and in the evening we have a talk from Barry Sanders. And I would like to also mention that Kadir Hoca is also trying to build some also kind of startup company on quantum technologies and filling in a very crucial gap in our country in this respect. So maybe today he can also mention a few words about these challenges as well. So we look forward to listening him. Kadir Hocam, whenever you like, you can start the lecture.
Thank you very much for this nice introduction and the nice organization, to organizers as well. I'm trying to share the screen. Can you see?
Yes, we can.
Okay, so basically today I will be talking about the need for the quantum key distribution and the countermeasures on the quantum side, what can be done and what has been done so far. So, and tomorrow I will be continuing with the experimental challenges, details of the experimental setups and practical applications. So basically the title of the talk is, so since it is two different, so this is kind of the ABC of the quantum key distribution. So the cryptographic security threats and the QKD as a solution to these problems. So let's define with defining the cryptology. So it consists of two class of studies, cryptography and cryptanalysis. Cryptography is basically trying to provide a secure communication and cybersecurity in general terms, let's say. And cryptanalysis is the opposite of it, trying to break the code and get the key and listen to other people, intercept the signals, etc. So for cryptography, we can divide it into two subclasses: symmetric encryption and asymmetric, or in other terms, public key cryptography encryption schemes. The most common examples of symmetric encryption is the advanced encryption standard, which is the AES. Nowadays, we use this one for symmetric encryption. For the asymmetric ones, the most common one is the RSA. There is also this elliptic curve cryptography. And the cryptanalysis, there are passive and active attacks, but I will not go into details as our main focus is on the cryptography side. So when we analyze a crypto system, there are 7 items that we need to pay attention to. The first one is the message that we want to deliver. Without message, cryptography doesn't mean anything. Encryption algorithm and the decryption algorithm, number 2 and number 5. These are symmetrical, the same thing basically, if we are using symmetric encryption in the opposite sequence. Encryption key, encrypted message, which is established by mixing the encryption key with the encryption algorithm, and then we use the message to have the encrypted message. So, and then we need to also consider the eavesdropper, because we cannot consider crypto system without checking the security aspects. So cryptography has been known for a long time. There are early studies about this. So the one example is the hieroglyphic. You know, these ones from the pyramids and, you know, like this ancient Egypt. And then the Caesar cipher is something no better. So Cleopatra was using one of these schemes for communicating with the Caesar. Caesar provided this key. Key is 2, for example, for this example. And then basically what you do is in the alphabet, you shift the letter with number 2. So if it is A, so the B, C, right? We just shifted 2, then it becomes C. So if we do the same thing for all the letters, we have an encrypted message here. So the key here is 2, and the encryption algorithm is shifting the letters in the alphabet with the number of the key. So this is the simplest example of the symmetric algorithm that I can give right now. So as you see, attack at dawn, a military command, say suddenly becomes something that we need to decipher. So, and then there's stenography. So burying some features, some symbols, signals, inside the paintings and all these things. There are common examples in the Renaissance paintings, for example. And if you know this Da Vinci Code, the movie and all these things, so you must be familiar with these things. And then there's a recent one, beginner cipher. This is a little bit more advanced version of the Caesar cipher, actually. So now the key is a word or something. For example, this is the place that I'm located at this location in Pakistan right now, Natia Gali. So N is 14, A is 1, T is 20. So if we have this message, for example, that I get 1, so N plus A, 1 plus 14, it becomes 15. In this case, it becomes O. The first letter becomes O. So that's how we do the encryption. You can keep using the same signal over and over again. So that is the core of the beginner cipher, but it can be also like dynamic. The key is not static, like, one word or something. It also changes from time to time. Date and location, all these things may also be used for key. So for symmetric cryptography, I must say, like, this cryptographic scheme is very common in the Cold War times. People were using this very commonly, and there were spies. Let me just give you an example, for example, if I can find. Yeah, so for example, this is a Russian one-time pad used for symmetric encryption, which was captured by MI5 dish. So basically, the Cold War times, you see these agent things so common because they were used for delivering the key for encrypted communication. And the security of this communications crypto system is relied on the secrecy of the key or secure delivery of the key to two parties for communication, and the randomness of the key. The key has to be random. So for example, this is not a good key because there are 3 A's, for example, in, I don't know, like 10 letters or something. Yeah, 10 letters, and 3 of them is A. So this is not a good way of creating a key. It should be totally random. There should be no pattern. And the secrecy is the most important one. And so that was a problem. That's why the certain number of people should be spies or couriers to deliver the keys to securely deliver the quantum key. And then once the computers had this certain computational power, that crypto scheme has changed to asymmetric, or in other words, public key cryptography schemes. In public key cryptography, there's a repository. You have to trust the repository, okay? They are the one announcing the keys. Just announce the numbers, and from the announced number, the sender 1, or let's say host 1 and host 2, understands which key they will use for communication. So for example, if the repository announces the public key for host 1, the host 1 uses this number for encryption, and host 2 knows this key as well. It uses for decryption. And if communication demand or secure communication demand comes from host 2, it gives the other number. Actually, other number is used for decryption and encryption. This is actually relied on this mathematically one-way difficulty problems. The most common ones are prime factorization problem and the discrete logarithm. So discrete logarithm also, like, it can be simplified to a similar problem like the prime factorization. Eventually, it becomes a period finding problem. So what is the problem if there are these nice crypto schemes working fine? The problem is there are quantum computer studies recently, and they can effectively use Shor's algorithm to find this prime factorization problem because they have some exponential speed up compared to the classical computers. I will talk about the details of this RSA and this public key crypto schemes a little bit more detailed. But so when I was giving this kind of talks, like, I don't know, 7 years ago, 8 years ago, someone in the room working in the cryptography field would definitely ask, well, you're trying to find a solution to a problem that doesn't exist yet, which is fair, actually, fair point. So we don't even know if the practical quantum computers will be ever built or not. Most probably yes, but it's not even sure. So, but we don't know when. So does it make sense to spend so much efforts on finding some solution to a problem that doesn't exist yet? The answer is yes right now, because NSA is the National Security Agency of US. It's, in the movies we usually see CIA, but CIA is just, all times, Cold War times, it was important. Right now, NSA is more important because it's dealing with the signal intelligence. And NSA published this question and answer announcement in 2016. You can find it, it's publicly available. Usually they provide crypto suits, and they say, like, within the next 30 years, there won't be any technology being developed that can break these codes or decipher the crypto systems. So they say 5 decades in this state, but it's 30 years. But they also said here that, we cannot promise that anymore because the people are studying quantum computers. If practical quantum computers being built, maybe they don't announce this. And if we don't know about this, then the crypto systems are not secure anymore. Therefore, we do not give such a guarantee anymore. This was a big, impact actually on the grants and the efforts on the quantum key distribution systems. So, but we know that asymmetric key public key cryptography systems are not secure against the quantum computer assisted attacks, but symmetric ones are secure. In a way that, the quantum computers does not provide an exponential speed up. I will give an example of how powerful term is exponential. But for symmetric algorithms, they can only apply this force attack for certain search algorithms like Grover search. And in that case, it only provides a quadratic speed up, which is not that important because you can just double the key length and take a precaution against this kind of attacks. Therefore, symmetric algorithms are back on, just like this Cold War times. So just to give an idea how this quantum computer finds these keys, prime numbers so effectively, it's because the problems can be optimized in a way that quantum computer can solve effectively. So therefore, the quantum computer itself is very important, but at the same time, the optimization of the problem itself is very important. That's why this algorithmic part of the quantum computation is as important as having a quantum computer. So this is just to give an example how it works. It's just an analogy. Of course, it is not an accurate example. There's no quantum going on here. Just to show how the optimization helps solving the problem in an easy manner or faster manner. So as you read here, you can just follow with me. I mean, there's a Sultan, he has 1 kg of gold and consisting of 100 grams of this gold masses, slabs, and he wants to make 100 coins of each 10 grams. He distributes to 10 jewelers to make this, and then each jeweler makes 10 coins, which it will be 10 grams. In this case, everything should be fine, but the Sultan hears that, one of the jewelers had stolen one of the golds. In this case, he's making the coins out of 9 grams. And then he gets angry, and then he calls his vizier and tells the vizier that, and then he calls all the jewelers as well. The jewelers are in line, like 1 to 10, 1, 2, 3, 4, 5 until 10. And then asks the vizier to use this measuring device that you see on the picture only once, find which jeweler stole the golds. So this is a puzzle actually. I mean, it's an old one, but it's a nice one as well. So of course you need to do lots of measurements to actually identify which one is this. But what you can do is optimize the problem. I mean, if you have the opportunity, you optimize the problem by using it once, you can still do this. That will save time and, how would I say, computational power, effort, let's say. How does it work? So you just take 1 gold from the first jeweler, 2 golds from 2 coins from the second jeweler, 3 coins from the third one, and 10 from the 10 coins from the 10th one. So in total, you have how many? 55, right? 55, 10 times 11 over 2, yeah, 55 coins. And if everything was right, it would be 550 grams, right? But if, for example, the third one stole the gold, then his golds would be 9 grams, and there are 3 of them. Therefore, it will be 547 grams instead of 550. So if it is 545, it means the 5th one. If it is 540, it means the 10th one stole the golds. So you can just use it once, understand how much is missing, and then identify which jeweler stole. So basically, it's not only about like using the quantum computer and then write your codes and then it solves the problem for you. That happens in our classical computers, but not in quantum computers. You only have atoms, ions, or superconducting qubits. You need to know how to optimize the algorithm to solve the problems. And Shor's algorithm is one way to do this. So basically, I just gave this example to quantum Fourier transform is this, by the way, this measuring device. You need to optimize this to use this device just once. So and the quantum Fourier transform is the discrete version, quantum version of the discrete Fourier transform in the classical manners. So anyways, this is just an example of how the calculation can be optimized. Of course, you still need a quantum computer to do the final measurement. The measuring device here is the quantum computer, and you can do things a lot faster. We talked about the exponential speed up. We didn't actually spend time on how does it work. So let me just elaborate it a little bit. For example, the public key cryptography works the following way. There's a number n, which is announced publicly. And then once n is followed, let's say I'm communicating with Özgür Hocam. Özgür Hocam is going to use Q for encryption. I will use P for encryption. And when Özgür Hocam messages me, I know that he is using Q for encryption. I will use Q for decryption as well. So, and if you look at these numbers, 21 is the multiplication of the prime numbers 3 and 7. As you see, it gets more complicated. And then once there's a number here, there are no smart ways of finding these prime numbers. And these are still small numbers. RSA usually uses more, numbers with more than 2,000 digits. And these are the prime numbers that are found in like the years are found also given here. As you see, we need lots of computational power to find these kind of prime numbers. Of course, these are the public known ones. The repositories that I mentioned, just like NSA, NIST, these kind of establishments, they also have like superior numbers, but we don't know them publicly. But this was found in 2018, for example. I mean, you look at the numbers, which means the computers were powerful enough to go to this number, and the computation time is also critical here, because it takes a long time to find these numbers. So therefore, prime factorization is a good problem for encryption in this case. But now think about this quantum Fourier transform, Shor's algorithm, and the quantum computer. So the number of operations can be significantly lowered. I mean, this function here tells an idea about like what is the operation number. As you see here, for quantum computer, it's much straightforward. Like less operations can tell you what is the answer. If that is the case, if you have the infinite resources, of course, this is an approximation to find some numbers here. Instead of this many years, you can just find in 100 seconds if you have a really global quantum computer with full capabilities. You can do this, at least potentially. So therefore, the quantum public key crypto systems are not secure anymore. And another, if I have to just give an example about the speed up, so like this is that hard, but I have another example. I gave you an example here that time can be significantly lowered.
Yeah, so how many qubits for this 100-second estimation?
Hocam, I just took some random numbers, so this I don't know. So that's why I said like having all the infinite resources, you can possibly reduce the timelines, something like this. So it's about actually just to give the ratio between them by looking at the operation time. I'm not like, see, it's not about actual simulation. So to give the exact numbers, I think it's a publication study. But the number of operations is exponentially decreased. That's why we can assume that with a finite operation time, gate operation time, we can provide an exponential speed up. Just to give an idea about what is the meaning of the exponential, let's give this example of the chessboard. The guy finds the chessboard, the satranch, the chessboard, and then the king wants to reward him with this one. And then he says, what do you want? And then he says, like, I just want rice. For the chessboard, the first square, I want 1 rice. Second one, 2 rice. Third one, 4. So like it just goes by doubling it, okay? So what would be your estimate that, in the last square, how many rice would be required in this case? So if you have to guess, I think our imagination is a little bit lacking behind the reality here. In the first row are 8 squares. We have 155 grains. This is still within our expectations. If you go to the half of the board, you already have around like 9 billion grains. This is more than a human can consume in their lifetime, roughly. And if you go to the last square on the board, 64th square, I don't even know how to read this number. I mean, honestly, I'm not trying to attempt to read. I just made another, again, very simple calculation. Let's assume that 100 rice is 1 gram. It means that that's 9 billion tons of rice. And I checked it, it's more than annual production of the whole world's capability. So exponential is that much. You just start with 1 rice, 2 rice, 4, and then once you go to the end of the chessboard, you have 9 billion tons of rice. That's huge. So that's why this exponential speed up is extremely critical. That's why people are spending so much efforts and money on the quantum computers. So now that we know that the problem is there, so what are the precautions that we are taking it? Of course, the simplest precaution is, well, if the quantum computer can attack the Shor's with the Shor's algorithm, it can attack the public key crypto systems, then we just find some other mathematical problems that the quantum computer cannot attack, right? That's very, very simple logic, straight logic. There are actually studies on this one, and there's a class of cryptographic schemes that people are making research about. And I really appreciate this kind of research because it's cheap. It's not like quantum cryptography. You don't spend much on the equipments. You just find a new algorithm. But there is one note that I need to make here. Quantum crypto, like people are spending so much money on the quantum computer and cryptography because there is Shor's algorithm. And Peter Shor is a physicist who published a paper in 1994. Right now, if me or Özyeğin, like if we find a new algorithm that can like actively attack this kind of systems, I'm not sure if we should or we would publish a paper about it, because now it's too critical. Like these kind of technologies are too critical. Therefore, if the new Shor's algorithms, if we don't know about them, or if there's a question mark about them, then how do we know that our new crypto scheme is secure against it? That is why these public key crypto systems that are based on other mathematical one-way difficulty problems, we were only using the prime factorization and the discrete logarithm. So if you find some other problems, so we don't know if there are some algorithms in some people's hands who has the quantum computer as well. But other than that, I think this is a very important branch of research scheme where you can take precautions against the quantum computer assisted attacks. So if we have to a little bit, give panic, so what can happen if the global quantum computers has the full capability that they can beat all the classical computers capabilities? Well, there are lots of risks areas. One of them is e-commerce, any field that requires digital signature, including e-devlet, banking industry, and defense industry, and then the cryptocurrencies as well. I know that there'll be a question coming about this, so we shouldn't spend money like invest money on the cryptocurrencies. No, you can, no problem. If I have a quantum computer, I wouldn't try to steal your Bitcoins. I would have some more important problems to try to solve, or more advantages on my side. That's why someone who has quantum computer would not be dealing with stealing the cryptocurrencies. So even if the security threat is there, I don't think it's the biggest significance. So the cryptography is a very important scheme, although we don't feel it all the time, but we are using it actively as public, as citizens, regular citizens. We are also using this. But of course, there are more important fields. So for example, there was an example recently, Germany, it was understood that Germany was trying to listen Turkey for a long time. It was a diplomatic crisis. So that's why like cryptography can be really significant. And if someone has quantum computer, they would try to do this rather than try to steal cryptocurrency. Okay. So what is the precautions? Sorry, before I continue this, Özgür, I cannot see time around me right now. So could you help me with the time? How much time I left?
Well, according to our schedule, it should be ending 3:15, but we can be flexible. As I said, there is only one talk in the afternoon session.
Yes, sure.
So can I continue, John?
Sure.
Okay, thank you very much, John. Thank you. Let's talk about the cryptography and summarize what's going on. There are two types of cryptographic schemes, symmetric and asymmetric. Asymmetric ones are called public key crypto systems. Asymmetric crypto systems are not probably secure because quantum computers can efficiently attack by using the Shor's algorithm. And the symmetric keys are secure, considered secure. By the way, quantum computers still have advantage compared to the classical computers for attacking the symmetric keys, but it only provides a quadratic speedup. Quadratic is not that important, okay? You can always take precautions by just increasing the key length. And the symmetric keys should be used as minimum amount of times as possible. So what does it mean? For example, if you have 128 bits of key, we shouldn't use it for 5 minutes of communication for this video transmission, because if you keep using the same key for encrypting the messages, one can apply the dictionary attack. So there is such a thing called dictionary attack. And to avoid that, you need to use the same key only for certain number of times. You should not exceed that. That means the quantum key distribution schemes should replenish the shared private key resources. So therefore, the key renewal rate should be as high as possible for the symmetric keys to be secure against the quantum computer assisted attacks, which should be fine, by the way. Just to give a little bit idea about like how does this work, maybe I should continue with this tomorrow if there's time limitation. Otherwise, I can continue, John. Okay.
I think you are fine with this. If you wish, you can plan to use an extended 10 or 15 minutes. It will
okay.
be fine.
Because I started late, so I don't want to. Thank you very much, John. Okay, let's start with the quantum mechanics. So it sounds scary, but it's something that human developed, and it's for humans. That's why you shouldn't be scared of any of these fields, including quantum mechanics. So let's just give a brief understanding of how this quantum stuff works and how the quantum cryptography provides some solution to this kind of cryptographic threats, security threats. So this is the famous Schrödinger's equation. It's mathematically beautiful. There's this complex. It's actually very similar to this classical wave equation, but it has this complex part here. And then the thing is, it's mathematically nice, but Schrödinger didn't know when at the time that he developed this equation, he didn't know the interpretation of this wave function. The interpretation came from Max Born. And he said, like, it could be its modulus square may give the probability of existence of a certain parameter within a certain interval. So just to give an example, let's say this is the x-axis is the position, okay, position axis. And then the y-axis is the modulus square of the wave function. And the modulus square of the wave function just gives some function like this. So if you want to find the probability of particle to be between the point A and point B, you just need to integrate between these points, and then that gives you the probability. If you put minus infinity and plus infinity instead of A and B, you just get 1, which means the particle exists. Okay, everything is fine so far. So, and then if we do a measurement, of course, it's more probable that we find the particle at A, but let's say we found at C. We did the measurement, particle at C. Now everything turns classical. We know the particle's position. It's at C, it's a Dirac function, delta function, and this function is limited with the Heisenberg uncertainty principle. But forget about it for the time being. Now we know that particle is at C. Everything is fine. So basically, once you do the measurement, wave function collapses, and then you have a classical position information. So the problem is, which was discussed in 1927 Solvay's conference. Recently, we have seen the new version of that one. In that conference, they were discussing where was the particle just before measurement was done. Let's say the measurement is done at time t. If we consider the particle's position at t minus epsilon, where would be the particle? So the first answer is coming from Einstein. It's a realist then. Didn't know it because the wave function couldn't tell it to you. Maybe the quantum is not a complete theorem, but it was somewhere. Whether you know or not, the particle was somewhere. You just didn't know it. Probability is it's something like this. I just flip a coin and then close it, and then ask you, is it heads or tails? So now you don't know it. It's 50% chance, but actually the coin has either heads or tails, right? One of them. It is certain, determined. Einstein was supporting this. And then the second answer is, this is actually Copenhagen interpretation. It's one of the main logics of the quantum mechanics came from Niels Bohr. Particle did not possess a position. You made it have a position by doing the measurement. So before the measurement, it did not have a position. It was a probability wave function. So I don't know what is the meaning of that. I still don't understand it, but somehow this is the correct decision because its interpretations are correct. And the third one is, so you're just asking, if you do a measurement before the measurement, where would it be is not a scientific question. So therefore, there's no meaning to discuss. This is not so valid. So this was not so valid. But there are still realist physicists right now today. We know that the answer 2 is the correct answer. So Einstein just gave an example to prove his point that, you know, quantum mechanics is not a complete theory. He just considered a spin zero particle, and in the case of two spin half particles. Spin half particles, just, you know, like you just think of a spin either up or down. If one of them is up, the other one has to be down, and vice versa. There are four conservation laws in the universe, and the angular momentum has to be conserved in this case. Therefore, if one of them is up, the other one is down. So then, let's assume that the blue one, so right now I'm in Pakistan, so blue one is in Pakistan, the other one is in Istanbul, okay? Red one is in Istanbul. And according to quantum mechanics, is 50% probability wave function. So before the measurement, they did not possess a spin. It's not that we don't know it. They didn't actually have it. So then, let's say Özgür Hocam did a measurement and then found it spin up. Then he knows that mine is spin down. And the thing is, you know, just before he measured it to be spin up, it was not spin up actually. He forced it to be spin up. Therefore, he did the measurement right on the spot. Mine is determined that it's spin down. But then how did this happen? So the information cannot travel faster than the speed of light. So then he was saying that the theory is not complete, or there is something wrong. That's why he says, okay, this is the, by the way, how do I say? First page of this paper, I forgot the term for that. It says like the scientists and two colleagues, basically Einstein, Podolsky and Rosen, find it is not complete, quantum mechanics is not complete, even though correct. So he's not saying it's wrong, but he's just saying that it's not complete, something that we didn't understand yet. Now today we know that, and then he made fun of it actually, and then he said spooky action at a distance in this, you know, paper, which means he was making fun of it actually. But today we know that, you know, these two particles, spin state is not independent two particle. We know that they are acting like one. So in physics, we know that it is just one entity. Their mathematical expression of their spin cannot be separated. We call them inseparable states. So they cannot be separated. So in physics, you can think of it like they are just like one particle. They are acting like one particle. So one of them has full correlation with the other one. So then in 1965, I think, John Bell thought of a Gedanken experiment, which means a thought experiment. I think your mind is still the best laboratory in the world. You should consider this. So basically, he just thought of this experiment where there are two entangled photons or particles. The P1 and P2 are the polarizers, and then you have the polarization analyzers here. You just analyze their polarizations, and then you basically do Einstein's thought experiment in a more closer to the experimental configuration. And then he found this algorithm that, you know, their polarization measurement outcomes in an algorithm should be less than 2. If Einstein was correct, which means before you actually put the polarizer and do the measurement, if the particles, the photons, do not possess a polarization, then in this case, it should be more than 2. It can be understood why it can be more than 2. But if they have some polarization, it's just we don't know it yet because we didn't measure it realistic. In this case, it should be less than 2. And we know that, you know, I think in 1991 or something, I don't remember exact time, it was experimentally proven for the first time that Bell's inequality can be violated. So now we do this every day in the lab. So that's something that we already know of, that, you know, we can get close to the Sivaldson bound. It means quantum mechanical interpretation was correct. They did not possess polarization prior to measurement. So actually, this has more meaning than what I just explained. So there's a philosophical background as well. So, you know, assumption, locality and realism. So according to this violation of Bell's inequality experiment, there should be no locality, no realism, or simultaneously both of them, like, which means there is no local realism. So, and the correct interpretation is proven by this experiment. Actually, so this is violation of Bell's inequality. If you see John Bell's experiment, and then in 1991, a young physicist understood that, you know, if you actually violate Bell's inequality, all you need to do is have another basis to do quantum key distribution, and that's Arthur Eckert. He found this. He published this paper in 1991, and his whole academic career was actually based on this understanding. So until that time, no one actually understood this. So entanglement-based quantum key distribution protocol, you just have one extra reference system, basis, basically reference system, that you choose for having the key, then actually while you are violating Bell's inequality, you're also doing quantum key distribution. Because of the time constraints and for you to have a little bit online search, I will just continue. But quantum key distribution is good in the sense that if there is an intruder in between and measures the state, the wave function collapses. And remember the wave function, we plotted that collapses, and now you have something classical, a Dirac peak. Same happens here, and then that Dirac peak, whatever the measurement outcome is, according to that, if you try to make another wave function, which means another state, we can never do this perfectly. We always leave some fingerprint that we did some measurement before. So that's called no-cloning theorem. So with this theorem, by the way, a violation of Bell's inequality, sometimes I keep getting the question that, which one is better, entanglement-based protocol or the BB84, which means no-cloning theorem-based or quantum bit error rate-based protocol. They are identical things, basically. Your state is collapsed, and you just have classical. So once you try to, according to the classical outcome, you try to get something quantum, you always leave some fingerprint. There's no way you can do it perfectly. So you either see it as a violation of Bell's value, S value less than 2, which means classical, or the quantum bit error rate is elevated at least 25%. So either this one or that one, depending on the protocol, gives you that there is an intruder as a third party eavesdropper or adversary in your system. So therefore, it provides the security for delivering the key to two parties. I would like to make one remark here. Quantum cryptography is not the correct term. I keep using it, I know, but it's not correct. There's nothing about cryptography or quantum cryptography. So there are symmetric cryptographic algorithms like AES. By the way, you're also using it on your WhatsApp. Like in many places, you use these encryption schemes. So what you do is you securely deliver the key so that you can use these kind of protocols. Therefore, the correct term is quantum key distribution. There is no quantum cryptography. Well, there are some quantum twirling and all these advanced protocols, theoretical proposals, but none of them has been observed experimentally. That's why quantum cryptography experimentally does not exist yet. It's just a quantum key distribution. So for prepare and measurement protocols, the most common example is the BB84. Entanglement-based protocols, the most common one is ACAT91 protocols. There are pros and cons for each of them. Entanglement-based protocol, basically it's difficult, experimentally difficult to create it, make it, because you are forming an interferometer. A quantum interferometer is more sensitive, double the sensitivity. So and for prepare and measure protocols, experimentally it's very easy, simple, straightforward to do it, but then you can only use it for quantum communication or quantum key distribution protocols. But entanglement-based protocols, basically you can use it for many things, even distributed quantum computing, like quantum internet, entanglement swapping, teleportation, all these advanced tests, you can do this with entanglement-based protocols. That's why if we are establishing a quantum key distribution setup, a network, I think it should be entanglement-based, because we don't even know if in the future, if we actually practically use these kind of networks for cybersecurity, but we know that they have some advantages. Entanglement-based protocols have some advantages that you can use for other tasks. So again, for example, let's say there are 5 stationary qubits in Istanbul, 5 stationary qubits in Pakistan right now, where I am. So we want to do a computation that requires 10 qubits. If you have a satellite that provides this entanglement in between, you can do your computation as if these 10 qubits are all together. So in fact, there is a large-scale project, 1.2 billion euros project, Quantum Internet Alliance. They're trying to make a pan-European quantum computer, let's say. But its capabilities is not only computation. That's why they call it quantum internet. It's a really nice approach to joint of this quantum communication and quantum computation fields. Lots of networks. I will talk about them tomorrow. Satellite projects. I think I can kind of stop here, Hocam. Continue tomorrow with the experimental configurations of the problem. Thank you very much for listening, and sorry for the delay again.
No, thank you so much. So we have some questions for you, Kadir Hocam, in the chats, if you can read them.
We constantly see, what is the question, right? Announcements of some company achieving the highest number of qubits. We also have access to quantum computers and write quantum algorithms. That's correct. For example, we can implement Shor's algorithm with IBM's Qiskit. However, we haven't solved AES RSA yet. My question is, at which point we can crack encryption with an available quantum computer such as IBM's? Can you also comment on the current computational power? Yeah, that's a very nice question, by the way. I will give example. So I will give example with the Human Genome Project. When people, the computers are developed and they want to like decrypt the human genome, right? Understand the genome sequence of the humans, and they were expecting around 2 million genes on the human. Considering our complexity compared to the other animals and the plants, that's what people were expecting, around 2 million. But it turned out that a banana has 36,000 genes and we have 22,000. So ours is less. Then how can be so complicated? How can we do so complicated tasks? It's the now we go back to the quantum computation problem. It's not about how many qubits we have. It's about how functional each qubit is. So for example, let's say we have 10 qubits. Do you have each qubit have some interaction capability with the other qubit or not? Or just each qubit is only interacting with the qubit in the neighborhood. So if that is the case, your computation capability is limited. But if everything is fully functional, you can access any qubit and interact with any other qubit inside this system, then that gives you another degrees of capabilities. So for example, all these, if you look at this IBM's Qiskit, the computer, so they also have this drawing of this chip, the superconducting qubits. You see that they are not having the connection between all the qubits is not there. Some of them, they are not talking to each other. They have to talk to each other. So this is one of the DiVincenzo criteria. So we don't have engineering standards for quantum computers because we don't even know what they are yet. We're trying to understand that they are very new, but we have this DiVincenzo criteria. And one of them is the qubits should be interacting with each other. Another one is like the qubit, when you're not doing calculation, it should not just decay somewhere else. Like you're doing something and then like this one is just going away. You need to bring it back and then continue your calculation, which is error correction. So that's another problem. Your decoherence time is very low, so we need to enhance them. So there are lots of problems, but the number of qubit is just only one problem among, I don't know, tens of problems. So therefore, the qubit number is important, but not the only important thing. So basically, a 50 qubit computer can do better calculations than 100 qubit computer. That's possible. I hope that answered the question. And then,
well, if they like, they can continue to ask in the chat, or hopefully they can also send an email to you if they want to discuss more. So we can proceed to the other questions.
Okay, I see this next.
Seval wanted to ask a question loudly.
About the Murathan Altay's question, right?
Yes. Seval.
Okay. Yeah, this was, I think, a very nice question as well. Can it be wired or wireless or both? Doesn't matter. So about the quantum computers, let me give it this. Okay, the superconducting qubits, they are in microwave domain. If you use ions, atoms, all these setups, they are in the optical domain. Optically, it's fine because we can have entangled photons and have the mediators between them. So therefore, we can do it wireless, no problem. The communication between two distant qubits, we can do it wireless with photons. That's perfectly fine. But for microwave, we cannot travel use these microwave photons because microwave photon energy is so small that we cannot use them. It's beyond our capabilities. What we need to do is convert them to optical wavelengths or infrared, then use them, and then in the other side, wherever we want to transfer, we again convert them to microwave and continue. So that's why for superconducting qubit-based technologies, we need these microwave to optical converters. And there is a technology that has been studied, but the efficiencies are still low, like less than 1%. I think it was 0.1% was the best value or something. They're not that practical. So if we have these nice converters with high efficiency, even the superconducting qubit ones can be wireless. But let me tell you one thing here. When we say wireless and all these things, just remember, all the quantum computers will need some like really good computers to operate all these things. So I'm just talking about the interquantum computer communications capable, like interactions, all these things, yes, they can be done wirelessly. For example, neutral atom-based or ion-based, trapped ion-based quantum computer studies, they can be done with photons. You can send to satellite and then communicate with another computer.
Thank you. Firstly, thank you for your nice lecture. I have a question. I want you come back to Alice and Bob examples, please.
Yeah, okay, I'm sharing the screen.
Here. Yes.
Where was it? Stop me.
Mm-hmm.
Okay. Yes.
Yes, here.
Okay.
Entangled photon is going to from Alice to Bob. It can be it objects to some mixed states, and it means changing information. It means changing of information from Alice to Bob going, and how can the purity of this entangled photon from mixed states?
Okay, for the entanglement, you need a pure state.
Mm-hmm.
Okay, mixed state means they are separable, right?
Yes,
entangled
photon, one entangled photon is going to from Alice to Bob. It's subject to mixed states. It can be, it can subject to mixed states, and information can be changed.
No, okay. So, for example, let me try to find if I have the scheme here. I will try to show it. Okay, this is the continuation of the tomorrow part. There's no surprise now. Anyways, I don't have it. Okay, so let's say you have a crystal creates HH photons, horizontal photons, and then there's another crystal, vertical photons. At the output, you have 50% chance that the photons coming are HH, horizontal, and the photons could be 50% VV, right? So this is not entangled state. This is a mixed state, which means they are separable. There are two entities. The first photon is, there is no correlation with the second photon. There is classical correlation, but not quantum correlation. So, but therefore, you remember this wave function is collapsing? That doesn't happen. So that is an example of mixed state. So if you want to have an entanglement state, that is a pure state, which means you cannot separate, well, not pure state, let's say inseparable states.
Namely, can we say that every entangled state is pure state?
Yes, you can say that, yeah.
Okay, I get it. Thank you.
But there is one thing I would like to mention it as well. You may have multiple degrees of entanglement, which means one photon can be two photons can be entangled in many degrees of freedom. Okay, there are 6 different ways of entangling the photons, as far as I know. There may be other ones, maybe I missed the literature. And in one study, 4 of them, maximally 4 of them, were carried in the photon, like in one setup. Okay.
Okay,
you get what I mean? So one photon is carrying 1 bit of information in this case, right? So that can be up to 4 in one study, and theoretically, we can go up to 6 different configurations, like, which means one photon can carry 6 bits of information. That is huge, by the way.
Okay, thank you. I have mixed this situation with entangled distillation.
Okay.
Okay, thank you very much.
Yeah, thank you.
So maybe let's take one more question before ending the session. Cengiz Hoca has one question in the chat.
Cengiz Hocam asked the question. Should we choose that one, Hocam?
Yes, he has some privilege, no?
Okay. Okay. What is the single biggest hurdle holding QKD or other quantum cryptography approaches from becoming widely used? What breakthrough is needed for widespread use of post-quantum or quantum cryptography approaches? I think, Hocam, intercontinental quantum key distribution is formed, And we know that we can even do this with the practical rates, which means we can actually use this. The problem is, how do you deliver it to end user? So when you have a satellite, for example, delivering the key to Earth, 2 locations, they are delivered to the optical ground stations. From there, you will need to have fibers or something to the end users, which is not easy task. I think the biggest problem here is the quantum repeaters. If we have repeaters, we can arbitrarily extend the distance, and we can also deliver to end users without any problem. Just like, okay, because we are having the analogy from the telecom fibers, you know, for example, Türk Telekom has this fiber network. Why don't we use it for quantum key distribution? Because they have relays. Every 100 meters or something, they measure the signal and then amplify it and then send again. That's what the relay does. So we have lots of relays between like 2 parties communicating in this fiber networks, like classical telecom networks. But we cannot do this in quantum. Once you measure it, the quantum properties are gone. So therefore, we need some quantum repeater, which means that can do this without causing some fingerprints. So to do that, we need a quantum memory, basically quantum repeater. Once we have this, they can be used as relays. But then there is this problem. I mean, people try to study quantum repeaters out of cold atom setups, BEC, you know, like all these expensive things. Who wants to put relays like that? So it's not practical. So it's nice to study these things, but the quantum repeaters are not practical in a sense that you can only do them in the lab. You can show them in the lab. I know Erhan Salamürek has really nice works on that one, but you know, you cannot just take their lab setup and make a relay. Too expensive. So for these technologies, I think they can only have certain like limited use, like a campus, limited campus area use or something like that. And to do that, I think we need quantum computers to be a real threat. So that people actually want to use this. But again, not the public. I mean, I don't think we will ever be using quantum key distribution for, you know, secure communication. But some clients for the banks, you know, like really large scale, they are using, for example, couriers to bring the key, the hard drive, so that they use this for authentication, and then they do the transaction. So for them, for example, definitely a quantum key distribution would be a cheaper solution than having this courier network. So therefore, I think it's about the use case. Like, I don't think everyone will be using the quantum key distribution ever. I'm not sure if that. Thank you.
Yeah,
Thank you, very nice question. Thank you very much.
Very good answer also, and thank you so much, Kadir Hocam, again. So please also make a note of the other questions in the chat before you leave, because I can see several more very good questions. So you can contact them by email, or they can access you via email. So I'm also happy to see that we are cracking some ice with the audience, and we are getting more and more questions after each talk. So let's keep this trend on, and we will see you in the evening session. Thank you for your participation.